Hello, class. Today we're going to go into part 2 of our study of our history of the understanding of the atom. And I just want to do a quick review of what we learned yesterday. We first started off with Democritus about 460 BC, and he's the first one that came up with the idea that atoms existed. Now, of course, he had no proof, but he, through his observations, very brilliant with the observations he was able to see, the experiments he was able to do, to realize that matter really consisted of these things called atoms. Atomos is what he called them, or indivisible, that were the smallest pieces you could make. He then next was followed by Aristotle. Aristotle was a very brilliant, very influential man, and he did not believe that there were atoms. And because he was so influential, we did not even begin to look at this idea for about another 2,000 years. We then talked about Lavoisier. So in the late 1770s, he was doing some experiments, and he was doing these reactions inside these containers. So he knew everything was contained. If you think about the candle that we did earlier in the year, that wasn't contained when I burned it, right? The gas of the candle, it evaporated, the reaction products of that, it floated away in the air. We didn't measure their mass. But he did his in a closed container so that nothing could escape. And he started to realize that whatever the mass was before, he had the same mass after. So you could still have that chemical reaction. Things changed, but the mass did not. So he came up with the idea of the conservation of mass. He was followed not too long thereafter by Joseph Proust, and he was working with water, and he noticed that every time he would break that water molecule apart, he had two things we now call hydrogen and one thing we now call oxygen, that they always had that proportion. Always had that proportion. And that started leading us down the track that, well, if we have the definite proportion of things, that must mean there's some there's something there. We must have something that makes up that hydrogen and something that makes up that oxygen. And that started leading us back to the idea that maybe these ideas of atoms existed. There's some small indivisible piece, because every time Proust broke apart the water, he got two hydrogens and one oxygen. And finally, that led us up to John Dalton. And what he did is he really put everything together, packaged it up nicely, and then people were like, oh, yeah, that makes sense. And he took, in his first point was kind of a combination of what we got from Democritus and Lavoisier, in that matter is composed of atoms, and these atoms are indivisible and indestructible. They're conserve their mass, right? Whatever atoms you have before, the atoms you have after. We can't change the mass. Dalton added the concept of 2 and 3 here, that all atoms of the same element are identical, while all atoms of different elements are different. And he finally included what Proust was doing with the law of definite proportions, that there was always a ratio when we're talking about a compound. Right? That compound always had that same ratio. Again, this started leading us to the idea that there was something called an atom. And that takes us on to where we are today. Well, somebody asked Dalton, what did he think about atoms? What would an atom look like? Well, from Adam's first point in his model, he was like, well, they're indivisible. You can't break them apart. So Dalton's thinking, well, if you can't break it apart, then we can just think of it kind of like a marble, right? Just a solid sphere. There's no structure to it. It's you can't break it. It's a marble. It has no parts. Well, this is the early 1800s, but by the end of that century, we started to learn a little bit more. This idea was starting to fall apart. And this goes to what we were talking about earlier about a model. The more we learn, the more complex our model gets. So here's the next step in the complexity of our model. J.J. Thomson was working with something called a cathode ray tube rather. And this is kind of a picture of one. And if you look at it over here on the left side, we have a wire coming in and we have a negatively charged plate. And on the right side, we have a positively charged plate. There's actually a little hole in this positive charged plate. And what they knew at the time was, we call this a cathode ray tube. This is actually the predecessor to what, if you ever saw an old TV that was really thick, or an old computer monitor that was really thick, as opposed to the flat screens we have today, they had something very similar to this, an advanced version of a cathode ray tube. And what would happen is that if you hooked up these plates to, say, a battery or a very strong high voltage source, the anode here, the negative part, it would emit some rays. We couldn't see them, so we just called them rays. And they'd come through, they'd go through the tube, they'd go through this anode here with the hole, and then they'd come and they'd hit this screen over here. Now, the screen had a special coating on it so that when the cathode ray hit it, right, it would glow. You'd see kind of a sparkle. And J.J. Thomson was investigating this and trying to understand what was going on. And what he was seeing was really the first part of evidence that there's something more fundamental than just the idea of an atom being a marble. He found the first part of an atom. Well, what did he do? So he was playing with this cathode ray, and he noticed that if he put another pair of plates, a positively one here we have in the top, a negative one here I have in the bottom, that he could bend this cathode ray. So as he put this charge on here, he would see on his screen, instead of it hitting straight in front of the tube, he could see that he could bend it. He could move where that ray was hitting the screen, and that led him to understand that, wait, they knew about electric fields at that point in time. That helped him understand that there must be something here that's got a negative charge, because we can bend it, we can move it with an electric field, and because it bent towards the positive plate, that must mean it's got a negative charge, right? Opposites attract, so the positive plate's going to attract that negative electron. The same repel, right? So this negative plate down here is going to repel the electron. That's what we called it after he figured out what it was. So he figured out that there's this part of an atom that we're going to call an electron, and that it has a negative charge. This was a huge, huge step in our understanding of the atom. We're no longer, as it's indivisible, we actually can find pieces of it. We already talked this unit about electrons and protons and neutrons. So again, I was just saying he took this stream of particles between these two charged plates, and you could see that they were deflected away, that the particles would be bent towards the positive plate. Because they're bent towards the positive plate, they must have a negative charge. Okay. So here's another picture of a cathode ray. Again, we can see here on the left, it's coming out. Here we have a gas that's glowing, not too dissimilar from a fluorescent light bulb. And as the electrons or the cathode rays are flowing through this tube, if we put a charge or a magnetic field or an electric field, we can see that it bends it down. Now, if I did a little video of this, we could take this little plate you here see up here at the top. We could move it around, and we could bend this ray. You would see it actually bend down, bend over, and up. We could move it around simply with that electric field. Very, very significant and important discovery, because it really told us there's a lot more to this atom than we've been thinking so far. So somebody then asked Thomson, well, what do you think an atom looks like? If it's got these parts, it's not a solid marble, what might it be? And J.J. Thomson came up with this idea of a plum pudding model. Now, he was British. Plum pudding is a common dessert in the British world. For us, we're not too familiar with it, so I kind of like to think of it more as being like a chocolate chip cookie. And what he said was he thinks that the atom is kind of like this plum pudding, or let's say a chocolate chip cookie. Instead of plums, let's say chocolate chips. And our chocolate chips represent the electrons. They got a negative charge. But Thomson was also smart enough to realize that the atom was neutral. It didn't have a charge. So if we had these things called electrons that had a negative charge, something else must have a positive charge. So in his model, the plums were electrons, the pudding or the bread that's kind of around there, more like a cake, that must have a positively charged, that must be positively charged. So my example of a chocolate chip cookie, the chocolate chips would be negative, but the cookie dough, the cookie itself then would be a positively charged medium. That positive charge is spread throughout. So now we've got the idea there are pieces and parts of our atom. Very big difference. We're learning more. More knowledge, more complex our model's getting. Well, not too long after Thomson, then Ernest Rutherford came through, and he did an incredible experiment that we call the gold foil experiment. Very influential in changing our understanding of the atom. Now, how did this work? So if we look down here in the bottom right of my picture here, there's this box. And in this box, he put a substance he knew would emit these positively charged particles. Positively charged particles. And he made a little hole in this box so that when the particles were bouncing around, they didn't go anywhere. But if you had a hole, they could escape. So it's kind of making like a laser beam here. Or think of kind of like a bucket. If you got the bucket full of water, but you poke a hole in the bottom of it, then that water is going to come shooting out that hole. That's kind of like what we're doing here. So these alpha particles are flying out of this hole. And what he expected to do is he had those lined up so they'd go through this real thin sheet of gold. And then surrounding this gold, he had a screen, much like we did when we talked about the cathode ray, right? So that if a particle went through this gold and then it hit the screen, it would make a little flash, it would make a little spark. And we could see where the alpha particles were hitting our detecting screen. So what he was thinking was that he shot 20,000 of these alpha particles at a sheet of gold. It's quite a few. Well, and he could count them, right? You could look at the screen, the deflecting screen. You could count them 1, 2, 3, 4, 5, right? So he knew how many were coming out. But he got up to about 20,000, and then he noticed something really weird. One of those particles bounced back. So the 20,000 he saw, they were all mostly right over here, straight across, opposite of the box, through the foil and straight through the foil. They were mostly right over here. But after 20,000, all of a sudden he saw one, and it bounced almost back to the box. This was really bizarre. How could that happen? How could that happen? That didn't make sense to him at the time. And here's another kind of a picture of what he was doing, showing you the screen and the gold foil, and of course then our box with our alpha particle emitter. A little close-up of the foil that we're using, and then here, instead of having the screen around it, they had these more advanced things. These are photomultiplier tubes. They're much more sensitive to the charged particles coming through. And we could put one here in the back straight through, and they put a counter on it. How many times did that tube detect one? And then they had another counter over here, and they could move this. They could swing it around at a different angle. They could see they got a much higher rate straight through, but every once in a while they'd get one that would bounce back. So when they had their other detector kind of on this side, on the alpha particle side of the foil, you'd see one every once in a while. So why was this so astounding? Well, if the plum pudding model was correct, right, then we basically had plum pudding with negative charged plums, or a chocolate chip cookie with negative charged chocolate chips, that these alpha particles, these positive alpha particles, would just simply go straight through. As long as it was thin enough, they would just go straight through. What did he see? Right, we saw, instead of them going straight through, we saw some, 1 and 2, 20,000, actually bounced backwards. Bounced right back at him. So this was really kind of interesting, because here's what they were thinking, that at the time, they knew they had these alpha particles, and let's just say we took, went to a bowling alley, we took a big old bowling ball, think of that as being our alpha particle, and when you roll it down, you throw it down the alley, what's going to happen? It's going to hit those bowling pins, but it's basically, the bowling ball is going to go straight through. It might knock the pins around a little bit, but the bowling ball is going to go straight through, right? And that's why that big catcher at the back to catch the bowling ball. But what happened here instead was, instead of the bowling ball going through, at the bottom, he saw the bowling ball kind of hit that foil, hit those pins, and it bounced straight, almost back at him. Bounced right back at him. We've never seen that. If any of you have gone bowling, you don't see your bowling ball bounce back. So Rutherford would spend some time thinking, well, why would this be the case? What could explain this? Because now he had some more knowledge. How do we improve our model? And he came up with a conclusion that there must be something called a nucleus. Now, how does this work? What does he know about the nucleus? And the first thing, he came back and he said, well, the nucleus must be very, very small, because only 1 in 20,000 of the alpha particles hit it. So in this case, let's take our bowling alley kind of perspective, and let's take our bowling pins, and instead of making them so close together, let's spread them far apart. So they're really, they're not close together. There's a big distance between them. So, or another way, let's make our bowling pins really, really skinny. Really, really skinny. So our bowling ball, it can roll through them. Most of the time, the bowling ball is going to miss. Right? It's going to go right through those pins because they're so skinny. 1 in 20,000 might hit a bowling pin and bounce back. But the significance here about it bouncing back is that if it bounced back, that told us that our nucleus had to be positively charged. It had to be positively charged, because if it was negatively charged, it wouldn't bounce back our alpha particle. right? Because opposites attract. The positively charged, if the nucleus had the same charge as our positive alpha particle, it would just attract the alpha particle. It wouldn't deflect it. It wouldn't force it backwards. It wouldn't repel it. So it must mean that our nucleus is positive, that it was able to make our positive alpha particles bounce backwards. And finally, the third part here, that nucleus must be really, really dense. Even though it's very small, it must be really, really dense. It must have a lot of mass towards it. So let's think about that. If instead of taking a bowling ball and we rolled it down the bowling alley, what if we took a little BB or a tiny, tiny little metal sphere, maybe a tenth of an inch in diameter, something really tiny? If we were to roll those down the bowling alley, what's going to happen? Well, again, they're very small. They're going to miss. The vast majority of them are going to miss hitting any of the bowling pins. But if one did hit the bowling pin, what's going to happen? Is it going to go through that bowling pin? Is it going to knock the bowling pin in the back like that big, massive bowling ball? No. That little BB would bounce straight backwards at it. What that tells us is that the nucleus here had to be much, much more massive than the alpha particles we were shooting at it. Or similar, just like my bowling analogy, that the bowling pin or the nucleus had to be much, much more massive than the bowling ball or the alpha particle that was running into it if it was able to make it bounce backwards. Right? If the alpha particle was more massive, had more mass, it would go right through. But it must have had less mass, and that's how we come up with the idea of our nucleus. It must be small, very, very small. It has to have a positive charge because it's able to bounce things backwards, and it must be very, very massive. Again, if it was able to bounce things backwards. So they asked Rutherford a little bit more, well, what does that help you understand about the atom? Now that you come up with this concept that we have a positively charged nucleus, it's very small, very dense. And he came up with the idea that our atom must be mostly empty space. Mostly empty space. That kind of goes back to what I was talking about the bowling alley. Let's take our bowling pins and let's move them really, really far apart. Right? Maybe have them fill the whole bowling alley, all 20 lanes or 30 lanes or something, and just have one bowling pin in each. But I could really take that analogy a little bit step further. And from what we know now, we can use the idea that if you look at the tip of a ballpoint pen, that little ball, if we go out to the football stadium and put it on the 50-yard line, right in the middle of the football field, the closest electron to that nucleus, if you will, make that little ball, that ballpoint, the nucleus, stuck in the middle of the football field, the closest electron to it would be clear out on the track. So think about that empty space between this ballpoint at the middle, this ballpoint ball at the middle of the football field, and all that space between that and the track. That's a lot of empty space. And that's now where our understanding of the atom has gotten to. Well, that's it for the second part of our lecture. We'll continue on after the holidays. We have 3 more lectures. We're going to talk a little bit more about how our understanding of the atom has evolved and gotten more complex as we've gotten more information. Please don't forget today's 3-question lecture quiz, and have a wonderful holiday, and we'll see you next week. Take care. Bye-bye.